Guys, welcome to our new video, and this will be my last video of Trie Data Structure. And as you already know, if you see my previous video of Trie Data Structure. So, what is Trie Data Structure? If you have no idea, you can just go to my YouTube channel and see my previous videos. Okay, but still, for those people who are new, I can explain little bit, but in this video we will go further advance in Trie Data Structure. Okay, so what is Trie Data Structure? Trie Data Structure is like a tree like data structure used to store strings efficiently. It supports fast prefix search, auto completion, and dictionary operations. Okay, these are the main use cases of trie data structure, and each node represent a character, not a full string. Okay, and the time complexity is O of length for insert and search. Okay, and we have these is the internal structure of trie node. So what is trie node? Trie node typically contains children, pointers, links, array or map. We use array. So how many children's can a node has? Like 26, because English has only 26 characters. So in total we have 26 nodes. Okay, and then because we are not repeating any word. Okay, so a b c d e f g is 26 characters, so we have only 26 children pointers. um, and then end of word we have a flag which is true or false, and then optional we can also use frequency count, like how many times the word like occurs. Okay, so these are the operation which most commonly used in trie operations. Okay, one is insert. Every data structure has insert, update, delete. So it has insert, which is O of L, and then search of L as well, and then we have start with prefix, which is OL as well, and then we have delete and then autocomplete. Okay, so if we go, and these are the types of trie data structure. One is standard trie, and which we are already implemented in our previous video. And then second is compressed trie, Radix tree or Patricia tree, and then we have Suffix Trie, then we have Suffix Trie, and then we have DAWG, which is directed acyclic word graphic. Okay, so what are these? Before going into deep, I will further go with the trie data structure. Okay, so we have a good example here for trie data structure. Let's suppose we have word and dad and two. Okay, and we have this root node on the top, which is implemented in red color. So every trie data structure has one root node, and then we have, you see, there's a children child node which is a, and then we have a children child node which is n, and then green shows that the word is not complete. It's n is not a word, and is a word. So at the end you will see its color that shows it's true, it's a complete string. And so in other cases, like if you want to store and, you will make a new a here and then n and then t. Or if you are doing like, using arrays or whatever, linked list, you have to store separately, right? And but here the beauty of trie data structure is you store a only one time and one time. So the thing is, at the end of like two strings, d is and t, that differentiate these two strings. Okay, so we use a and d and a and t. So if you search here, you will easily find and. Okay, so it's quite easy. You save plenty of space in your tree data structure. It's easy to implement, it's easy to search, it's easy to delete is quite easy. So how are you going to delete in this? So for example, you cannot remove the nodes, right? It's a pointers, right? How are you going to remove? It's quite headache. So let's suppose if you want to delete and, if you, at the end of this string you will see that its color that shows is true, it's a valid string. So if you make it false, So the and is still exists in the tree, but if someone search in the tree, it goes a n, and then it search for d, it search for t. When they search for t, it will found false. That means and is not a complete string. So it might go further after t, but t has no child. So you will never find and if you delete this, like mark as false. So it's quite simple, you know. And on the other hand, you will see dad and do also store in the same tree. So it's a separate tree, right? A and d, a and t. So that's quite. If we have another string that starts with c, we will make a new node from the root node. So every children, like every alphabet will you know, you start, if the initial is not exist, like if the string not starts from a d right now, we will make a new root node. Make sense? So it's quite simple, you know. And now if we go to the further, like other types of trie data structure, that's a standard trie, which is use fixed size. As I told you, it's 26 children's. And then fastest operation, high memory usage, best for small alphabets, right? If you want a string like further long strings, then it might not be the best case. The second we have compressed trie, like which is Radix tree. Compressed chains of single child nodes save memory, use in IP routing and compilers. Okay, what does it mean? So the compressed trie data like trie Radix tree is basically chains of single child nodes that are compressed into one edge. Greatly reduces memory use in IP routing and compiler. So instead of saving, like let's suppose you have save, you save and right? At the end you see D and T is different, right? So what we're gonna do is we don't, we don't store full alphabet. Okay, so we use like after a, you have T here and then D here, we will make a new node here. Like after a, we will not store after n or d, we will make after a. So like you understand what I'm trying to say. Yeah, it's quite hard, but instead of storing full a and d, a and t, we will use n and t after a. I will further go into deep so you will have an idea what I'm trying to say. Okay, so mostly tries use in normal cases, but if you have autocomplete, then we use these advanced as well. So so the compressed try stores, you see it's and we basically combine these two words at the end, like n and t, and then stores it quite, like it's used in compressed data structure only. Okay, and then we have it was why it's useful. It's useful because we use it save a lot of memory, faster traversal, and then it has use in routers and compilers and IP indexing. Okay, and then the second one is we have, which is suffix tree. Okay, suffix trie, sorry, my bad. So suffix trie is basically it a trie of all suffix of a string. So for example, if you want to insert banana, okay, what you gonna do? We use b a n, right, banana. But for suffix tree, we store like banana and then remove b a n, and at the end a. So it's used in substring cases. For example, when someone's enter, just give me the banana substrings. Okay, so it will show all the you know substring, possible substrings easily. You don't need to write any algorithm, nothing. You just call this suffix tree and it will return. Okay. But the problem is, downside is huge memory usage, and then pattern matching, lot of complex algorithm. So, but you can use that as well. Okay. And then we have suffix tree, which is like a full compressed version of try. Advantages is like, it's much smaller than suffix try, extremely powerful for searching, and you can find like patterns in off n. Okay. Also, it's used in compilers. You see, in Radix, where we have to go through all the string into compiler in a Regix. If you heard about Regix in compiler construction, you will have an idea. Text editors and bioinformatics. Okay, and the last, not the least, which is DAWG, and it's basically advanced compressed version of try. It merges identical subtree, save massive memory. It's used in basically dictionaries, word games, scramble like scramble, and then predictive text models. You have seen, in some apps, you type some word and then you have prediction of those words. So it can be possible by using these. And then real world application of tries, Google search autocomplete is a very good example of try. And then Google ID, and then IP routers, compressed trees, Patricia, basically Radix tree, used for fast routing lookup. And then, if you want to search like DNA prefixes stored in tries, it's a good example. And then dictionary and word games, also efficient word lookup. Okay, so I hope you understand what is try and what is the compressed version of try data structure. So in my next video, I will further explain how we're gonna implement try data structure and some of the advanced. Okay, so stay tuned with us and like, share, and subscribe. Thank you for watching.